looking at tin wall pressure vessels, and I have sketched here a tin wall pressure vessel showing a pressure P being applied. Right, so normally we would have an outer diameter, inner diameter, right, and just some terms, mean diameter is really the average of the two, right? Our wall thickness would be the subtraction of both radii. So that would be our wall thickness. Now, we talk about tin wall, and how do we know what is a tin wall and a thick wall pressure vessels? Right, so one way we do that, or the way we do that, we say that the ratio of your mean diameter to your thickness should be greater than 20. Right? And if it is this holds true, then we could say we have a tin wall pressure vessel, and the calculation that we're going to do could be valid. Right? So what we will do, we will start by looking at a stress element. Right? So let's look at the stress element that we've been drawing since the introductory lecture. Now we are customly being sigma x and sigma y. Right? But in this case now we have, because it's a circular shape or circular coordinates, it's not x and y, it's the hoop direction and radial direction. What I mean by that, the hoop direction is this direction that goes around, and the radial direction is the direction that goes out. We also have the longitudinal direction, which is along the length of the vessel. So those are our three directions. Right? Again, three directions is hoop, radial, and longitudinal. Right, so we have our bursting pressure, as we call it. This is our hoop stress. That is hoop stress, or our bursting stress. And you call it bursting. I mean, it's just a layman's way of saying that we're going to keep increasing the diameter of this pressure vessel. Right, now the other stress is in the radial direction, sigma r. Right, and this is our radial stress. Right, so this is looking at it on the pressure vessel if you were to cut a slice straight. If you look at it from this end here, then we have our longitudinal direction, longitudinal stress, and our hoop stress. Right, our radial stress will be coming out of the page in this case. Right, so in a tin wall pressure vessel, we make the assumption that that radial stress is approximately equal to 0. And that's because we see that the material is so thin, and we have, this is our radial stress. The material is so thin, and because we have a free surface, the sigma r at that surface is equal to 0. So therefore, that variance of stress between that very small slice of material is next to nothing, so we assume it to be 0. Alright, so moving on. So we need to be able to calculate this hoop stress and then that longitudinal stress. Alright, so for the hoop stress, right, what we do, we assume that we cut the pressure vessel, we cut the surface of it. Right, so we assume that we cut the down the end here. Right, so we have now a pressure that's being applied. that's trying to open this pressure vessel. And we have an area, right? We have an area here in which that pressure is being applied. So that area here would be, remember this need to join these, this is length, and then we have the diameter D. I remember we're ignoring the thickness of it. We're ignoring that the diameter is different from the inside to outside. We're just going with a nominal diameter. Actually, inside diameter and outside diameter is very close to each other. So we're just going to use D diameter. And so this area here would be D times L. Right, so that is the force that is being applied due to the pressure. Right? Now that force, remember everything is in equilibrium. That force must be counteracted by the force in material. Just like in the beam and bending moment. We have a moment being applied to the inside the beam, so our bending stress must be there to resist that bending moment. Right, so in this case here, we have a force being developed, or a stress, I should say, being developed in the material, and that stress, we call that stress the hoop stress. Right? And the area in which that hoop stress is being applied would be your length by your thickness, right? Because remember the material is thickness T. And we have two of it. We have on both sides. We have here and we have here. So it will be 2 L by T. Right, so we could say now that we could balance. We say that the forces are in equilibrium. So we could say pressure by area dl is equal to the sigma hoop times that area. Right, so that's, remember, let's keep in mind force is pressure times area. So you could actually calculate now. You could say sigma hoop therefore is equal to P dl on 2LT and this is our hoop stress calculation. Right, so the next stress is the longitudinal stress. Right, so if we look at this pressure vessel again, right, we see now that again we have pressure being applied out. Right, so we looked at the pressure bursting the pipe in the outward direction. Now we're going to look at the pressure pushing it in the longitudinal direction. Right, so that pressure must be counteracted, or that force generated by that pressure must be counteracted by a force in the material in that direction. And we're saying that stress is longitudinal stress because, again, longitudinal direction. So the area in which this thing is being acted on, so this area here, where the pressure is being acted on, that area is right, so that area would be pi d squared on 4, right? And then this area now, that has been applied in the material, that in which that stress is being applied to any material, that area would be right. So remember again, we say the diameter inside and outside is close to more or less the same, right? So if you were to kind of if you have a page that is roll up and you unroll it, it will be the length times the thickness. The length is diameter by pi, right? Circumference by the thickness t, right? So it come like we have, this is the, right, and then we just kind of unrolling it out slowly. And this length here, we know that this length here is diameter by pi, and that's the thickness. So that's the area, pi by diameter by thickness. Right, so we have again balance of forces. So we have pressure by pi d squared on 4, which is sigma longitudinal by pi by d by t. Longitudinal therefore is PD on 4t. So that's the longitudinal stress. So you notice that your hoop stress is on 2t and longitudinal is on 4t. So the hoop stress is 2 times the longitudinal stress. Right? Now, if you look at a sphere, right, a sphere, either which way, anywhere you cut a sphere, it will look like this. Right? So if you cut it on top, well, anyhow you cut a sphere, it will look the same. Right? And in this case here, your bursting pressure or the resistance to prevent the material from bursting or the vessel from bursting must be a longitudinal stress. So for a sphere, your hoop stress is equal to your longitudinal stress. Right, so therefore the stress in the material of a sphere, a spherical pressure vessel, is always lower than if it was a long pressure vessel. So this is why you would see in situation where you have a very high pressure situation, high pressure pressure vessel, like for example transporting liquid natural gas, LNG. If you were to go down point 14, you would see a lot of circular, on these ships that filling up LNG, you would see a lot of spherical pressure vessels. And that's because the pressure, as we see here, is a lot less, well, half of that if the pressure vessel was shaped like this, like a traditional tank.